If you've ever used an AI image or video generator, you've experienced a unique kind of modern magic. You type in a few words, a simple phrase, like a red apple on a wooden table, and in seconds, something incredible happens. Your text, your idea, is sent to the heart of the system, the AI model. For now, let's just think of this as an opaque, magic box. We put language in one side, and the model's job is to process that language and generate a completely new, visual representation out the other side. It doesn't search for a photo of an apple. It creates one from scratch, based purely on its understanding of your words. The result is a transformation from abstract language into concrete pixels, just like that. A coherent image that matches our description. But how? How does a machine read red apple, understand what a wooden table looks like, and combine them into a scene that makes sense to us? That's the question we're going to answer. In this video, we're going to open up this magic box and see exactly how the AI turns our words into worlds. To start, we first need to understand how the model learns to speak our language. So we have our prompt. But how does a machine, which only understands numbers, begin to grasp the rich meaning behind words like apple or wooden? It can't read in the human sense. Instead, it has to translate our language into its own. The very first step is to break the sentence down into smaller, individual units, a process called tokenization. Think of these tokens as the basic vocabulary the AI works with. It looks at the prompt not as a whole sentence, but as a sequence of these individual pieces. Now comes the magic. The AI uses a powerful component, often a text encoder like the one found in Clip, to convert each token into a special list of numbers. This list of numbers is called an embedding or a vector. It's essentially a coordinate, a specific point in a vast, multidimensional meaning space. Each token is mapped to a unique location in this space. The incredible thing is that the text encoder is trained on billions of sentences from the internet. Through this training, it learns the relationships between words. For example, the encoder learns that words like red and apple are conceptually related. They often appear together and describe a common object. As a result, it places their numerical embeddings very close to each other in that meaning space. We can visualize this as them being semantically close. The mathematical distance between their vectors is small. On the other hand, what about words like red and table? While a table can be read, the conceptual link is much weaker than between red and apple. The model knows this, and so it places their embeddings far apart in the meaning space. They are semantically distant. This numerical representation, which captures not just words but the web of relationships between them, is the crucial translation that allows the AI to understand the intent behind our prompt. This set of embeddings is the input for the next stage of the process, where the visual creation truly begins. So, the AI now has a rich, numerical understanding of our prompt. But how does it translate that abstract meaning into a visual masterpiece? It doesn't start with a blank white canvas like a human artist might. Instead, it begins with this, a canvas filled with pure, random noise. Think of it like television static. Every pixel has a random value. This chaotic grid is the raw material, the block of digital marble from which the final image will be carved. Now, this specific pattern of noise isn't just random chaos, it's a very specific starting point. To understand where it fits, we need to introduce a concept central to modern AI, the latent space. Imagine a vast, high-dimensional library or map. We're showing it here in 3D for simplicity, but in reality, it could have hundreds or thousands of dimensions. Every single point in this space represents one possible image. Images that are visually similar, like different photos of cats, would be clustered together in one region of this space, while photos of cars would be in another. So, where does our noisy canvas fit in? That entire grid of static can be represented as a single point within this latent space. There it is. Our starting block of noise is just one coordinate on this immense map of possibilities. The AI now has a starting point. But where does it need to go? It needs to move this point from the region of random noise to the region that represents a red apple on a wooden table. This is where our text prompt comes back into play. The numerical embedding we discussed earlier acts as a guide, a vector, a compass. It creates a text guidance arrow in the latent space, pointing from our random starting point towards the target region that matches the prompt's meaning. The AI's job is now clear. Follow this arrow. In the next part, we'll see exactly how the AI takes its first step on this journey, using this guidance to begin transforming the chaos into coherence. Well, at its core, a video is simply a sequence of images, or frames, shown one after another. So, a video generation model starts in a similar way, but instead of one canvas of noise, it works with a whole series of them, laid out across time. This is where a critical new idea comes in. The model isn't just looking at patches of pixels in 2D space anymore. It's now considering space-time patches, small cubes of visual data that have a width, a height, and also a duration in time. It's analyzing a block of video all at once. Now, the model can't just create 3 beautiful but random images. If the first frame has a ball on the left, the second can't have a car in its place. They must be connected logically. This is the principle of temporal consistency ***. The model is trained to understand that the content of one frame heavily influences the content of the next. It learns the physics and logic of our world, that objects should persist and motion should be smooth. So, when the denoising process begins, it's not happening frame by frame. The AI is looking at the entire sequence simultaneously. For every patch, it's asking not just what object should be here, but given the object's position in the previous frame and its likely position in the next, what should this patch of pixels look like right now to create smooth, believable motion? It sculpts the entire block of spacetime from noise into a coherent scene, all at once, and the result is a sequence where the object, in this case, a simple circle, moves logically from one position to the next. This consistency is what separates a true video generator from a simple slideshow of disconnected images. By understanding and enforcing these relationships across time, these models can create the stunningly realistic and dynamic videos we're beginning to see. So, having explored the key ingredients, let's put it all together. In this final part of our journey, we'll map out the entire process, from your words to a final, stunning visual. It all starts, of course, with the text prompt. This is our instruction, our creative command to the AI. But how does a machine read our intent? First, the prompt is fed into a sophisticated text encoder. Think of this as the AI's language comprehension center. Its one and only job is to translate the complex nuance of our words into a precise mathematical form called a guidance vector. This vector is a rich, numerical summary that captures the essence, the objects, the styles, the actions of our request. This is what will steer the creation process. Now, for the canvas. The AI doesn't start with a blank slate. Instead, it begins with a field of pure, random noise, like a television set with no signal. This static is the raw material, the block of digital marble from which the final image will be carved. With our 2 key inputs ready, the instructions and the canvas, we arrive at the heart of the system. This is the diffusion model, the engine that performs the iterative denoising we discussed. It takes the random noise, and using the guidance vector as its map, it begins a meticulous process of refinement. Step by step, in a repeating loop, it subtracts a small amount of noise, each time looking at the guidance vector to ask, does this look more like what the user asked for? With every pass, recognizable shapes and patterns begin to emerge from the chaos, like a photograph developing in a darkroom. After many steps of this guided refinement, the noise is completely replaced, and what remains is the final image or video, a brand new visual that faithfully matches the description in our original prompt. And there you have it. From a simple text prompt, through language encoding and iterative diffusion, to a final, coherent visual. This elegant pipeline is the fundamental architecture that powers the incredible AI image and video generators we see today.